Okay, hi. In this session, we're going to talk about a couple of non-3D advanced imaging methods for comparison with some of the 3D methods that we're talking about in more detail at this summer school. So I'll start, and then Alicia will give a second example in a few moments. So I'm talking about RTI, which is reflectance transformation imaging, which is not quite a 3D imaging method, although it has some things in common with 3D imaging, as you'll see. And it's sometimes, the term is sometimes used interchangeably with PTM, which is polynomial texture mapping. Although in normal use, RTI is the method of capturing these images, and polynomial texture mapping, PTM, is the format that is produced by this method. And there are other ways of producing PTM files as well as RTI. What RTI is effectively is virtual relighting of an object. It's sometimes called a 2.5D method because it's slightly more than two-dimensional, but it's not quite three-dimensional. And it is basically the process of using light from different angles, different elevations on a surface, to illuminate different features of that surface. This is very similar to how people trying to read inscriptions, for example, have always viewed or photographed inscriptions by casting raking light on them. So casting light from a very oblique angle that causes the texture on the surface of the object, the inscribed letters or relief images to cast very sharp shadows and be visible. And if you cast the raking light from several different angles, you capture different parts of the surface. Similar in some ways to photogrammetry, but a different method of capture. In photogrammetry, you move the camera between taking each shot. In RTI, you keep the camera stationary, but you move the light source between taking each shot, which gives you different views of the same exact same surface. It's a relatively cheap method, although not quite as cheap as photogrammetry. You do need a good camera, and you also need a good focused light source, preferably a light source with a focal length of infinity, so it's not spreading out, that you can move around. The most common and the highest quality way of doing RTI is using a dome, which has multiple light sources embedded in it. And where those light sources are fixed and their locations known to the software that processes it, and therefore no special measurement is needed. The dome makes it a little bit more expensive. The cheapest dome that you can get to do RTI with costs somewhere in the region of £1,000 to £2,000, I think. You may be able to get cheaper ones, and you can get DIY ones that you can make yourself. I think that the cost is coming down all the time. There's also a method that's called HRTI, or highlight RTI, which doesn't require a dome and therefore is a little cheaper. And what you do with this method is you have your camera stationary on a tripod in front of your object, and you have your light source, which would be a portable high-powered flash lamp of some kind, attached by a string to the object, so that as you move the light source around between each photograph, it remains the same distance from the object. And when you're using highlight RTI, you need to put a reflective spherical object close to the object that you're photographing, something like a black billiard ball, for example, and that enables the software, as that ball appears in every photograph you take, to calculate the angle that the light source was at when that photograph was taken, and it does all the various calculations and is able to make some extrapolations about the surface texture based on that. And we'll talk a bit about how that works in a second. There is plenty of free software around for processing all those photographs into those RTI photographs and images into your PTM. You do need a specialist viewer, although there are several viewers around now. Most of them are free, and there are even viewers that you can embed into web pages, so you can view them there. But you can't just open a PTM file in in your desktop computer without specialist software installed, all of which is quite big. Basically, the way this works is that as you're taking the photograph, your camera, as you say, the viewing location, as shown in this image, which is an image borrowed from culturalheritageimaging.org, who are specialists in RTI, both in training and in capture. The light reflects from the object at different angles, and therefore at different intensities to the location, depending on the angle of the surface where the light strikes it and the angle at which the light was originally. So you get these surface normals, as it were, these reflections back from the surface, and this is captured. But because the photography is a 2D image, it's captured as a 2D image, but a 2D image with various different angles of reflection of those light back to it, and those images combined, you can extrapolate back to that 3D image from the previous image there. But it is still nevertheless a 2D image. It's just a 2D image with many layers and slightly different angles of light at each particular point on the image in each of those layers. So RTI is good for capturing relatively flat surfaces. That is to say, an object of which one surface is of interest per set of photographs, such as inscribed surfaces with writing on. They're very good for visualization of that surface. They're very good for helping you to read letters that might be very hard to read. They might be very shallow. The surface may have been worn in the hundreds of years since they were inscribed. They're very evocative. It's very similar to, as I said, how people normally try to view and photograph inscribed surfaces with raking light and so forth. And so it's quite intuitive to people who are used to reading this to say, oh, I'm just going to move the light source over a bit and see if I can see any better this way. It is, however, not a volumetric or really a 3D imaging method. There is only one visible surface available in each process, and the whole process of creating and taking these images and processing these images into RTI is quite intensive. It takes a certain amount of time, and it uses quite a lot of processing power to do so. A little more than photogrammetry, I think, and there's slightly more specialist equipment and software needed for it. I'm going to, just for this, very briefly after this final slide, to show an example, again taken from the Cultural Heritage Imaging site. This is a close-up of an object that has been imaged using RTI, and I don't know if you can see where my mouse is in this image, but I'm just moving the light source with my mouse. So the light source, as you can see, is moving around on this image. So this is it's still a 2D image, or rather a series of 2D images, but by moving the light source around, so I now can't see where my mouse is myself, but there it is. I can make certain features more visible in some locations than others. Okay, so that's the general principle of what a PTM looks like when you produce that. But I think I'll hand over to Alicia for the second example now. Go ahead.
Cool. Okay. Yeah. Thanks, Gabby. Okay. So let me just full screen. Okay. So yeah, I'm just going to talk briefly about another 2D imaging application, which is multispectral imaging. So this captures image data within specific wavelength ranges across the electromagnetic spectrum. So it can allow extraction of additional information the human eye fails to capture with its visible receptors for red, green, and blue. So as humans can see the RGB, when you apply filters with ultraviolet or infrared or X-ray and combine these filters into a photograph, you're able to capture more information. So this is commonly used in the fields of archaeology and cultural heritage, specifically in remote sensing and in document or painting analysis. So for remote sensing, it can be implemented into GIS programs using satellite imagery that multispectral filters are applied to. So again, the combination of different wavelength filters allows for the visualization of archaeological features not visible to the human eye. So it allows for identifying and mapping archaeology without the destruction of excavation. So you can see from this photo here, the RBG image, you can kind of make out outlines in the field. In this 2019 image, it's hard to see anything. But when you go to the hillshade or thermal, these combinations of filters allow you to pick out a lot more in the landscape and see archaeological features, which are still below ground. And multispectral imaging can also be used on a smaller scale. So for example, with paintings. And this project applied multispectral imaging by embedding 4 spectral bands into a standard RBG image. So the wall paintings from this Tomb of the Monkey, an Etruscan tomb in Italy, it was enhanced using this technique so that a number of details on the painting could be made more visible, as you can see the difference between the 2 photos here. So there are quite a few benefits to multispectral imaging. However, like we said, this is not a 3D method. It's really only good for single visible surfaces. It's also quite expensive, especially when you apply it to remote sensing. And it does require specialist knowledge for applying these filters and identifying features that come out from using these. And finally, it can create very large data sets. However, with both MSI and RTI, since they are photography-based methods, you could theoretically combine them to use them with other 2D photographs and implement them into 3D imaging. So maybe, Gabby, you have a little bit more to add to that.
Yeah, this, as far as I know, this is still speculative and experimental, but so you can, for example, you could do photogrammetry, where instead of texturing your 3D model with the simple 2D photographs you've taken, you could texture them with the multispectral imaged photographs. To have a 3D model where features of it are visible on the surface that are not necessarily visible to the naked eye, as Alicia was explaining. So that sort of combination of things. Obviously, that would be pretty data intensive, combining two already quite large data formats, together. The other thing that I know has been talked about, and I'm afraid I don't know if this has actually been tried, but it certainly sounds very promising, is using RTI as the 2D images for the surface texture of a 3D model produced by something like laser scanning, to basically texture a point cloud with RTI images, which would enable you to not only move the object around to see other angles of it, but also to move the light source on any one surface or multiple surfaces of that object, and see them in that way. So those sorts of things, although these are, we don't want to dismiss these as just 2D methods, because they add a lot of information in the process of imaging, which can be combined with 3D methods, I think. I don't know if as I say, I don't know of any concrete examples of either of those to share, and I think they are still both slightly experimental.
Yeah, I suspect in the future we may see more of these applications being implemented into 3D, so it's something to look out for.
Yeah, watch this space.
Yeah.
Great, thank you.